And can you see the screen as well right now?
Yes, I can see the screen.
Okay, so last time we stopped at the conditions of equilibrium. We were discussing turning effect of forces, and we talked about moments in general. We discussed this equilibrium and the fact that there are two different types of equilibrium, and we discussed those in detail. So let me summarize what we the only important things that I'll summarize, and then I'll ask you if you have any questions from the previous lecture. So far we have talked about in the last class, we discussed the principle of moments, right? Did we discuss it? Yeah, we discussed it, right? So can anyone tell me the main idea of the principle of moments?
The principle of moments is the states that if a system wants to be is an equilibrium, the sum of clockwise and anti-clockwise are the same.
Yeah, the sum of the anti-clockwise moments is equal to the sum of clockwise moments, right? So I can write it like this, something like this. Sorry, m anti-clockwise. So what this states and the condition this satisfies is equilibrium, right? So the principle of moments is simply telling you that for a body to be in equilibrium, or when you can observe a body to be in an equilibrium, in that case, the sum of the anti-clockwise moments is equal to sum of the clockwise moments, provided there is a pivoting point, right? And the pivoting point for both of these is the same, meaning that suppose if you have a rod pivoted at some point. Now, there could be anti-clockwise and clockwise moments on this rod, depending on the different types of weight. And so these different moments, the sum of all the moments, by all the moments meaning that there could be more blocks as well. So there could be more forces, and all of the moments of all of those forces should be equal to the anti-clockwise moments of all of those forces. So that's essentially the principle of moments. And then we did an example from where the key point was to tell you how can you solve these particular type of problems regarding the principle of moments, right? If you remember, we did this example, this one, right? And in this problem, we solved for the moments, and we saw conceptually also that which on what side would the turning effect of force be larger or smaller, right? And so the idea here is to understand how can we go about solving all these types of problems. And the what should I call it? I'll call it problem solving technique for problems regarding principle of moments. So the first thing is to obviously draw a free body diagram, right? So we draw a free body diagram, and we talked about these free body diagrams in a lot of detail in the last chapter, not really the last chapter, but in the chapter of dynamics. I devoted all of the lecture completely to free body diagrams, and that's because these diagrams are really important. These will help you to visualize or picture the situation, what is happening, or the problem. The second step is obviously you have to identify the pivoting point, so that you can say that this is that pivoting point about which any of the rotations or turning effects are going to happen. So you have to identify the pivoting point. What would be the next step? Anyone volunteer to?
To find the forces applied.
Exactly, right. So the next step is then you will look at all of the forces that are applied on the system. So you can write it as identifying the forces. All of the forces on that particular system. And of course, if you're identifying forces, then you're also identifying the directions of these forces, right? So because force is a vector quantity, but I'll write it and their directions. But even if I don't write this thing that you also have to identify their directions, it is understood that force is a vector quantity, and to completely specify a force, you need its strength and its direction. All right. And what is the fourth step? Anyone?
To
So you
calculate
have
the momentum. To calculate the
To
momentum.
to calculate the perpendicular distance from the pivot to the place where the force is applied.
exactly. So that's right. So of course, Tahor Muiz, you have to calculate the moment, but before you can compute the moment, it's force times the perpendicular distance, right? So far we know the forces, we know the pivot. The only thing left is to understand this perpendicular distance from the force to the pivoting point. So that's what we'll identify, right? So you can say something like you have to identify the perpendicular distance from the force. Again, perpendicular from what? Perpendicular from the force to what? The pivoting point, right? All right. And so the final step is to compute the moments, right? So you can compute the moments. You'll use this equation that force times the perpendicular distance. It's going to clutter up over here, so I'm going to write it over here. Force times the perpendicular distance, and this will give you the moment about some particular pivot for a force, right? And then the final step is step number 6. This is only applicable if the system is in a state of an equilibrium, right? So if equilibrium is maintained, then you can apply the principle of moments. Is that understood?
Yes.
Right? Because principle of moments is only applicable to systems where they are in an equilibrium state, the complete equilibrium state. All right. So that's more or less what we did in the last lecture as well. Is there any question from these things in anyone's head right now? Any question, anything that is unclear? Or
No questions.
okay. All right. So if there are no questions, then we can let's move on to the next and the final topic of this chapter, which is center of mass or center of gravity, right? So center of gravity. All right. So before we talk about center of gravity, It is, well, it's a center of, you can talk about center of mass and then just multiply it with the gravitational acceleration, and then it becomes center of gravity. But so you need to understand what is center of mass, right? So I'm going to start with this thing, center of mass. Any idea what it could be
It's
from the
the
name?
it's the center of an object where all the mass is mostly located.
All right, right. So as in one way or another, that's exactly right. Because whenever we're doing all of this mathematics, right? Um, it's very hard to completely specify. For example, suppose you have a person. Now, if I want to, maybe he's doing something, he's running. Suppose he's running, and I want to, there is some force on this person, he's accelerating or whatever, and I need to compute F equal the force on this person corresponding to its acceleration. What is the mass that I'm going to use over here? Think about it and then answer.
Center mass, I think. Center of mass.
Center of mass.
The mass,
Yeah.
the mass
Which
of the
mass?
ma
The mass of the object, right? But what
yes.
mass can should that be, right? Because think about this. The mass of this person, maybe he's running with his legs. Which mass is more corresponding to its acceleration? Maybe not all of its body is properly accelerating with the same rate. So the question here is, what mass should I take? The mass of its hand, the mass of his body, legs, or just some, it's, you have to include, you can say, all of its mass, but it's very difficult to include, to understand which mass exactly is accelerating by this much speed. So this is an example of a person. I can give you many more examples. Uh, but the idea is that we use this thing from mathematics, the idea of a point, right? And a point is something, it's not a physical thing, but it's going to help you in doing the mathematics. So we say that all of the mass of this object is located at a particular point. For example, this is the point, right? So we can now, what I can do is, I had this person, right? All this person, and I'm going to say that all of its mass is located at this particular point, and then I'm going to name this thing as center of mass. What it means is that now I can completely ignore the geometry and the topology of this person, and I can just consider this point, and I can say that this point is a person, which is something very odd, right, and mysterious. But we can do that, and that's how we have been doing all our calculations as well, by the way, so far. So we don't care about the geometrical structure of this human being. We just care about its mass, center of mass. So we say that all of its mass is located at that point, and now we can work with this point, saying maybe that this is suppose 75 kilograms, and then we can completely forget the body structure of this person, and then we can do some of our calculations, right? Because clearly this person is not a point object. That's, everybody agrees with that, right? The person is not a point object, but you can use this idea from mathematics of a point and simplify your problem. And because, for example, I'll also give you another example of a car. For example, consider a car. Here we have a car, and here are the wheels of the car. Just imagine that this is a car, and we do a lot of calculations for it. We can do a lot of calculations for this car. We can compute the forces on this car. the frictional force, the normal force, all these forces we can compute and everything. But what is the mass that I'm using? The mass that I'm using in all of these calculations is also the center of mass. You could again argue that, maybe, for example, a force that is specifically only acting on the wheels, you could have some weight from these wheels, some weight from, suppose, inside steering wheel, some weight from the chair inside, some weight of the person, and all of these. So it makes your calculations very problematic. It makes them very difficult. So we can just ignore all of these things, and we can say that all the mass, the total mass of the car, is just a point. Let me use some other color. Let's use green. It's this point, and everything, every mass that comes from this car, whether it's the mass of the wheels, the mass of the body structure, the mass of the chassis, the mass of the person, the mass of the seats inside, whatever it is located at this point, and this is known as the center of mass. And that's the center of mass that we use in the mathematical calculations that we do. And so what we can understand from that is that for a center of mass, it is a point where all of the weight or the mass of the body is situated. All mass is situated. Now, of course, that is unphysical, right? It's completely unphysical. You might argue that it does not make sense. How can you take a point which does not even exist? Because that's what mathematicians say. A point is something that does not exist. And then you can say, and then you're also saying that I'm putting all the mass of the person on that particular point, which does not exist. And if that point does not exist, then the mass cannot exist as well. And it seems bizarre. But the truth is that that's how you can do the mathematics with this idea, and it gives you the right answer as well. Right? So you can do it, and why not then use this idea when it makes life so easier for us to compute different things for this object, force, different physical quantities, really. So is that idea clear to all of you? Or
yes, clear.
Clear. Okay, that's very good. Now, in your exams or tests or whatever, you'll see a term used, a uniform body. Now, the idea of center of gravity is applicable to, a body that is uniform, which means that all of the mass is equally distributed at every point in that body, right? And what that implies is, a uniform body implies is that that's where you can use the idea of center of mass or center of gravity, and then you can perform all your calculations as well. Right? The word center of gravity or center of mass are used interchangeably. They are both the same thing, right? So at the center of mass, another important point is that at center of mass, the net rotational forces, I'm just going to call them rotational forces, which is essentially a torque. Torque is also, you can think of torque as moments, as we have been discussing. So you can say that the net moment is zero. It vanishes. There is no net moment at that center of mass, right? So, well, that's more or less what you need to know about the center of mass. And now you can let's work out some of these center of masses for different objects. Now, obviously, the question in your mind should be that, well, we have talked a lot about center of masses. How can I find the center of mass for various objects? So how can you find center of mass?
Is it located at the center of a body?
Not necessarily. I mean, think about this. You can say, in physics, we use words very, being very lazy, we assign words to things. It's not always at the center of the body. For example, I mean, you can argue that this could be a center of the body. For example, for a triangle, its center of mass is located, somewhere around here. You can now, before I go into that, to answer your question, I will. But let's talk about how can I find the center of mass. The very basic technique that you should know is simply that the center of mass of different objects is always located at the intersection of the diagonals that I can draw, right? So I'm going to write this, and I know at this point you might have not understood a word that I just said, but I'll explain it, right? So it's located at the point of intersection of the diagonals. What that means is that, for example, let's take a cube or a square, right? A two-dimensional shape, it's a square. I can draw diagonals on this square. What I mean by that is I'm going to take one point at this corner, and the opposite point for this on the square is this one, right? So let me use this color, right? And now let's join these 2 points by this line. Let's change it to blue. This is one diagonal, right? Now to draw another diagonal, I'll take one other corner of the square. Suppose I take this one. The opposite corner to this is this one. And so we have 2 corners again, a pair of these corners, and then we'll join them again with a line, a straight line, right? And let's make this line again blue. You can clearly see that these 2 lines are crossing each other. They're cutting each other at a point. And that point is known as the point of intersection. Intersection means that the lines are crossing each other, right? And they're crossing each other at a point, and that point is called a point of intersection. Just some fancy English assigned to the beautiful geometrical mathematics, right? This point, I'm going to make a circle on this, and this is the point, which is the point of intersection. And according to the statement that I made, this is the center of mass of the square. Let's do another exercise. Let's again come back to a second shape, the triangle one that I just drew before. And now I want you to tell me how. Let me call this 1, 2, 3. 3 different corners, right? Now I want you to tell me, how will I find the center of mass of this triangle? Go ahead. What's the first thing that I should be doing?
The point.
Anyone? Yeah.
The corner of the vertex of 1, where you have marked 1, to the midpoint of 2, 3.
2 and 3. Okay. So that's something around about here, right? My triangle is not a perfect triangle, so yeah, but this would be that point. Okay. So I'm going to now join these 2 dots, right? Okay. The next thing.
And the next point, the next line goes from point 2 to the midpoint of 1 and 3.
All right. So that's somewhere here. And then I'll just join these like this. Okay. One more corner is remaining.
Yes, from 3 to the midpoint of 2, 1.
2, 1, right? So the midpoint of 2, 1 is somewhere here. And then I'll just join these like these. So what you can see from this is that all of these lines intersect at one mutual point, and that point is this one. And this is the point of intersection, which means that this is the center of mass of the triangle. All right, let's do an interesting one. What is another shape that you can think of? Maybe a circle. A rectangle. A rectangle would be very similar to the square one, right?
Yes, circle is also fine. Circle
is fine. So yeah, any other shape?
A star.
A star. Okay. So for example, first let's try to do for a circle. How would I go about this thing? It has no corners. It has no corners.
No, circle has a. You can make a point on a circle and say it's a corner.
The diameters, where all the diameters intersect. The midpoints, it will be the center of
I mean, it would be okay. All right. So that's, but how can I find it? So I can take any point. For example, I can take any point on this circle, and suppose, you know, for because in the books you're going to see the points like this, and like this, and like this, and then they'll draw a positive like symbol, and then they'll say that center of mass is at the center. But let's take any other point, maybe this point. A point opposite, exactly opposite to this point, is a point that is over here. So these are the 2 points, and these 2 points would be joined by this line. Now let's take any other any 2 other points. For example, I pick a point over here. The point exactly opposite to this point is somewhere over here. And when you join these 2, you see, you again land at this point, which is the center of mass for a circle. You could have done exactly the same thing by taking this point, and the point opposite to this one would be this one, and then you would join these 2 with this line, and then you could have taken this one. Actually, I don't think you can see this color blue very well, so I'm just going to take green again. This one and this one would be the exact opposite to that, and then you can just draw. You can see that it again lands on that center of the circle, which is the center of mass, right? So is the idea of center of mass clear to everyone?
It's clear.
Clear. All right. Okay, let me check how much time do we have left. We have 7 minutes remaining. Okay, so now let's
Can we do a star?
A star. Okay, yeah, all right. So let's see if we have space over here. A star, defining the center of mass star is a star. You mean a shape of a star, right? So let me draw something like that over here. Let me see if I have a tool that can draw a perfect star. Let's see. Wonderful, that worked. So let's try to make this a bit bigger. Here we go. This is an interesting exercise, something even I have not tried doing before. So let's try to join two opposite points, right? So for example, what would be the opposite star? Let's start over here, this one, and the opposite point to this one would be what, in your opinion?
So it'll be between the two.
It will be the right
So
leg, I
how am
think.
I? So how can I? It won't be a leg, sir. So how can I point it, sir?
Oh, sorry. Actually, you know what I should have done is I should have done this thing. 1, 2, 3, 4, 5.
So it's between 2 and 3. 2 and 3. It's the point between 2 and 3.
Something like this. That's what you're saying?
Yes, sir. Yes, sir.
Okay, let's try doing this, right? Any other suggestion from Taha? Taha or
Uh,
Muiz, I think.
Is it 5 to 3?
5 to 3. I don't think so.
Yes.
Okay, so this is actually an interesting problem to do. I think I'm going to go after the class. I'm going to try doing it myself if we cannot finish it in the class, and then we'll discuss it in the next class as well. Because it's a very complicated shape if you think about it, right? So I'm going to do it as well, and then you guys also do it. All of you do this problem. Try to find the center of mass of a star, and then in the next class we'll start the class by matching all our answers. Even I'll become a student with you, and we'll match all our answers, and then we'll argue why do we think that our answer is the correct one and the other ones does not make sense, right? So we'll do that. So this is an exercise for all of you for tomorrow's Friday, tomorrow's class, right? So we'll discuss this in the tomorrow's class at the center of mass of the star.
Sir, we don't have a class tomorrow.
Why not?
Sir, it's Friday.
We do have a class on Friday as well.
Oh, okay.
Yeah.
I didn't know about the Friday.
Yeah, actually, due to some reasons, we did not have classes for regularly for the past 2-3 weeks, and so maybe that's why you got confused. But we have our class timings are from Monday to Friday. Sometimes what we do is on Friday we take a quiz. Sometimes it's a quiz that I tell you we are going to have that quiz. Sometimes it's a surprise quiz. And I know at this point, someone is going to come up by saying that we have not even gotten a solution to even one of the quizzes so far that you have given. Tomorrow, I'll not give you a quiz, don't worry. I'll give you the solutions to all the quizzes that you have done so far, right? I'll give you the solutions. You can match your answers. If you have any questions, we can talk about those in the class, right? Before the class, I'll hand you, I'll try to do it by tonight, if I can, right? I'll give you the solution to all of the quizzes that we have had so far. Sounds good?
Sure. So I think in a star shape, all the lines of symmetry, they meet at a point. So that would be the center of mass.
I mean, something you're talking about these things, right?
Yes, sir.
Yeah, so that kind of makes sense. That's something that I also had in mind. But let's keep it as an exercise, and then we can discuss it tomorrow, right? Okay, so let me just quickly see. I want to finish with the stability. Okay, so I'm going to quickly talk about stability. We have 2 minutes left. How can you tell if something is stable? For example, I mean, let's consider something. Let's consider a surface, and you have an object on the surface. I'm going to try to draw this object as Okay, so let's see how does that go. It's a pencil, right? It's a pencil. And we know that I'll just tell you that most of the mass of the pencil lies somewhere over here. So this is the center of mass. And so the weight of the pencil is something like this, right? And the pencil is pivoted where it meets the ground. So at this point, it is pivoted. What could you do? You could, just for fun, you could push this body from here, and that would make the body tilt, right? So eventually what will happen is that I don't think we'll be able to cover this in this much time, but let's try anyways. What would happen is that it would, something like this. It would look something like this. And this point is still fixed, like over here. Actually, it would look something like this. Now you can see the weight is still directly downwards. As long as the weight is directly downwards to its base, it will keep coming back to this position. But if, or for example, it's something like this, you can see that the weight does